An example of a function that's not differentiable. We've talked about what it means to be differentiable. We say if f of x is a function, we can calculate its derivative at a point using the limit definition of the derivative. And that's the limit of the difference quotient. So this is how we calculate a derivative. What I'm going to show you today is an example of a function for which this limit does not exist at a point, and so the function is not differentiable at that point. And the example I'm going to show you is the example of the absolute value function. Okay, so the absolute value function is a piecewise defined function, and it's defined, the absolute value of x is equal to x if x is 0 or bigger, and if x is negative, the absolute value gives back its opposite, so you get a positive number. So if x is negative, the absolute value of x is negative x. You've seen this function many times, so I'm not going to talk about it very much, but I will show you the graph. So let's plot this. So here's an x-axis and here's a y-axis. I'm going to choose green for the graph. So this is the graph of the absolute value function. Let's say y equals absolute value of x. There's two branches here, one for each piece in the piecewise definition of the function. Over on this side, we have a graph of y equals, that looks like y equals x. And over on this half, we've got a graph of y equals minus x. Both of those are nice linear functions. We've talked about the derivative of linear functions already. Those two pieces are differentiable. So when x is strictly bigger than 0, or if x is strictly less than 0, the function is going to be differentiable. The problem then happens right here when x equals 0. Something's happening right there that keeps the function from being differentiable. Okay, so I'll go through the calculations to show exactly why that happens, and then we'll talk about it for a couple minutes. So let's actually take this definition with us. So we can use it in our calculations. All right, so there's the absolute value function. So the way I want to start is we're going to differentiate on the pieces. So first I'm going to start by picking a point that's strictly bigger than 0. So I want to make an aside about that right now. So here, let me write, here's the real number line. Okay, and let's say here's 0, and here's x naught. So x naught is strictly bigger than 0. So when you say something like that, there's always going to be space. The strict inequality says there's always going to be space between x naught and 0. And so that means that I can create a little open interval around x naught where all the points in that open interval are positive. So what I want to do here is this. I want to show you that if I take small h's, then x naught plus h is still going to be in this little interval. So consider taking h's that are between negative x naught over 2 and x naught over 2. Then if I add x naught onto all of these, I get this inequality. And so simplifying on the left, I get x naught over 2 less than this, which doesn't change. And this over here is 3x naught over 2. But notice this right here, this is greater than 0. So it means all of the x naught plus h's are also going to be greater than 0. And I'm going to use that in a second. So let's calculate the derivative at this positive number. Well, here's the difference quotient. And now we know x naught is positive. So we'll just write it this way. Okay, so we got that. Now let's copy this to the next page. Right. So continuing. Now we know x naught is positive. So the absolute value of x naught is x naught. And I just showed you that x naught plus h is going to be positive when h is small. So the absolute value of x naught plus h is also x naught plus h. Okay. And then now I can just do algebra to simplify the numerator. The x naughts cancel. And I'm left with h over h. H over h is 1. And the limit of a constant is the constant. That's 1. Okay. So just to summarize here, if x naught is bigger than 0, then the derivative of the absolute value function is 1 at that point. Okay, so let's do the same thing for, not h, x naught less than 0. Okay. We're going to do a similar thing, that if h is small enough, x naught plus h is also going to be less than 0. So with that in mind, here I'm taking the derivative at my negative number. Okay, this is the definition of the derivative. And then we'll sub in the absolute value notation. Okay, and since x naught is negative, the absolute value of x naught is negative x naught. And since h is small, the x naught plus h is also going to be negative. And so the absolute value of x naught plus h is the negative of x naught plus h. And let's take this and move it to the next page too. And continue our work. So let's distribute the minus signs. And there you can see that these x naughts are going to cancel. And we're left with negative h over h. And h over h is 1. So we get a negative 1. And the limit of a constant is always the constant. So this is shown that if x naught is less than 0, the derivative of the absolute value function is minus 1. Okay? So that's shown the following. Okay, that's the derivative information for the absolute value function. Now, what's missing is what happens at x equals 0. Okay, so let's look at that. And that's the point where the function's not going to be differentiable. So let's calculate f prime of 0. Okay, that's the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. F, remember, is our absolute value function. So I've got the absolute value of 0 plus h minus the absolute value of 0 over h. And the absolute value of 0 is just 0, so we're left with this. So if you want to do naive evaluation of this thing, you see you get 0 over 0. Okay? So on the one hand, that makes you sad because you can't divide by 0. On the other hand, it makes you kind of curious because, you know, something interesting is happening when you get 0 over 0. Now, notice our h's go into 0. So 0 is our interesting place. And notice we've got this absolute value up here, and its definition changes at 0. It depends upon if h is positive or h is negative. So to calculate this limit, we need to do one-sided, or take one-sided derivatives. Okay, so let's calculate the limit as h goes to 0 from below of absolute h over h. So that's when h is negative, and so absolute value of a negative number is its opposite. So we get that, and you see the h's cancel, and we get the limit from below of -1, and a one-sided limit of a constant is just a constant. So that one-sided limit is -1. So let's do the other one-sided limit. Okay, the limit as h goes to 0 from above. So h is positive, so the absolute value of a positive number is just a positive number. So we do that, and the h's cancel, leave a 1. And the one-sided limit of a constant is just that constant. And so the limit as h goes to 0 from above of absolute h over h is equal to 1. So what do you notice? Well, these do not agree. The one-sided limits do not agree. Okay, so what does that mean? Well, that means that if the one-sided limits do not agree, then the whole limit does not exist. Okay, and if that limit does not exist, that means the derivative here does not exist. So we conclude the absolute value function is not differentiable at x equals 0. All right, so there, we're done. You now have an example of a function that is not differentiable somewhere. And we discovered that from the definition of the derivative, calculating the limit of the difference quotient, and showed the limit does not exist. And it's because the absolute value function is a piecewise defined function, and where those two pieces come together, something funky is happening. So let's look at this geometrically for a second, and then we'll conclude the story. Or this will be the conclusion of the story. Conclusion of the epilogue, anyway. So here's, I'll do the absolute value function here in blue. So y equals absolute value of x. So we've just discovered that the absolute value function is not differentiable at x equals 0. It's differentiable everywhere else, because everywhere else is just a straight line. Lines are graphs of polynomials. Polynomials are differentiable everywhere. No surprise. The surprise here is at x equals 0. Well, let's look at this at this in two ways. The derivative at a point is the limit of the difference quotient based at that point. And this difference quotient right here, this is an average rate of change, or if you like, the slope of a secant line. So the secant line, here's an example of another point on the secant line. So this here might be x plus h, or actually 0 plus h. Let's do this properly. So the secant line through those 2 points, they all look like this. And all of these secant lines, no matter what that h is, as long as it's positive, has slope 1. Okay? But now let's look over here at secant lines on the left. So this is for h's that are negative. All the secant lines over here look like that. And they all have slope -1. So the slopes, if you come from the left, are never going to be the same as the slopes if you come from the right. They're always going to be different, and that's what we were seeing in the calculation of these one-sided limits. So this is geometrically what's happening. I'm going to give you two more ways to look at this. Another way to look at this is if you look at the point and somebody asks you, what's a tangent line there? You might think, oh, I can draw all kinds of tangent lines at that point. And you would kind of be right. The thing is, in calculus, we want tangent lines to be unique because we want to assign to each point a slope of a tangent line. That's what the derivative is. You take a function, look at its graph at a point, and the slope of the tangent line at that point is the value of the derivative function at that point. Okay? The fact that the tangent line is unique allows us to define the derivative as a function. Here, for the absolute value function at x equals 0, you might be able to draw all kinds of lines that intersect just at one point. All those lines are going to have different slopes. So there's not a unique way to assign the value of a derivative at x equals 0. You can't define the derivative in the same way. There's just too many options. So we just say the derivative's not defined there. So that's a second way to look at this. A third way to look at this, and this is the kind of the way I want you to think about it going forward. There's a couple different ways that a derivative can fail to exist, but this is a really important geometric one. If a graph comes to a point, like a sharp point, that means the function is not differentiable there. Okay, and so this is what I want you to carry with you with respect to this absolute value function. Graph comes to a point, the function's not differentiable there. There's a couple other ways a functions can fail to be differentiable, but this is the big one. This one will really jump out at you when you look at a graph, and this is the one that is most interesting to us. Okay, so study this example, understand all the steps, and you'll be good. That's it for now. See you next time.